Okay, good to see you guys here. So just a brief reminder of yesterday's content. We discussed some of the mathematical properties that these orthogonal transformations had. So we found that the determinant has to be plus minus 1. The inverse of an orthogonal transformation has to be the transpose of the corresponding matrix. And we additionally saw that only determinants plus 1, that were equal to plus 1, would correspond to any physically possible rotation. And so we closed yesterday's lecture by starting on saying something about the generalized coordinates which would be useful for description of a rotating system. And we had previously discussed these directional cosines, but we saw that not all of them were independent because we had 9 of them. And there were 6 orthogonality conditions. So only 3 of them could be independent, or 3 functions of them. And so I suggested to you that what we could use as generalized coordinates for our context would be these Euler angles. And we have to introduce these angles in such a way that the determinant is equal to plus 1. So what we'll do, sort of our strategy for describing a completely general rotation in 3 dimensions, is to basically do 3 successive rotations with an angle phi, theta, and psi. So this is our starting point, the conventional XYZ system. And the first step is to perform a rotation with an angle phi, such that we take this XYZ coordinate system to a xi, eta, zeta system. So these are just Greek letters you may use. Okay. So here's the first step. We're rotating the system around the z-axis with an angle phi. So that these are the xi and eta axis. And so we see that the z and the zeta axis coincide. So according to this, we can write let me just add a vector sign to underline that this is a vector. So if this is a vector in the new coordinate system, and x is a vector in the original coordinate system, we have the following. So D is here some rotation matrix, which takes us from x to psi. That's the first step. But this is not a completely general rotation because we are just rotating it around one axis. With this kind of transformation, we cannot describe any rotations, for instance, like this, around the y-axis. So we need two more angles. So our goal is now to take this new system, psi eta zeta, to a primed system. So we're basically now performing a rotation with an angle theta, such that we're tilting this z or zeta axis to a zeta prime axis. So what we're doing here, I'm not sure it's really obvious from this figure, but we're rotating the system around this axis. So we started off by rotating the system around the z-axis, in the plane like this, and now we're performing a rotation around this axis. So we're tilting this angle, which means that the psi and the psi prime axis should be the same. And we get an angle here and here. So again, we know that there has to be some kind of orthogonal transformation or rotation associated with this. So we call this C, which takes us from a vector in this system to the prime system. And then the final step is to take us to the last or desired coordinate system, x prime, y prime, z prime. And by then we'll have performed 3 rotations, such that this should correspond to a completely general rotation. Oh, sorry. Something like this. So what we're doing here is that we're now performing a rotation with an angle psi around this zeta prime axis. So we're changing the coordinate system like this. So if these figures aren't exactly obvious, there's also a set of figures in the compendium, which you can have a look at, which describes these 3 steps of rotations. Now, we need some kind of matrix, orthogonal transformation, which takes us from this. Oh, sorry, it shouldn't be x here. Which takes us from this coordinate system to the last one, the primed xyz system. So we have 3 successive rotations, which corresponds to our 3 independent directional cosines. And all of them correspond to physically possible rotations, as we can see. And hence we know that the determinant of this should be 1, plus 1. Well, we can now combine all of these rotations because we know that 2 successive rotations is equivalent to a 3rd rotation, just in 1 step. So by combining these equations, we can write the rotation from the original system to the primed system as one effective rotation matrix, which is given like this. So this takes us all the way from the original system to the last system in one go, so to speak. So I guess the next question is, what are these matrices? We've just stated them symbolically and say that there's some matrix, D, which takes us from xyz to zeta eta, xi eta zeta. So do you have any suggestions for what D should look like? Like this?
Yes.
Okay.
And same for the next line?
Cosine again?
Yes. No sine.
Okay. And then cosine?
Yes.
Like this?
Yes.
Okay.
And then just once.
Just once? Like this? Okay, it's a good suggestion. So let's have a look at it. So according to this, we have that zeta should be equal to the lower row of D multiplied with this vector. Yeah.
There's a problem with this because the z-axis shouldn't be rotated.
Mm-hmm.
The D matrix does that.
That's true. So we can see this from writing out this expression. We would get x plus y plus z, which isn't exactly what we want because we have stated here that the z-axis should in fact be equal to the z-axis. So what we should have is just zeta equals z, We can obtain this by setting 0 here. In which case, as you say, the z-axis remains unchanged. So the 1 should be here, definitely. Are we happy with this now, or? So we also have, if this is correct, we have that zeta should be able to, we should be able to write like cosine phi x plus sine phi y plus z. Okay, you're not happy about this? Yeah. Because all we're doing here is a rotation around the z-axis. So this is basically a 2D rotation, right? Yeah.
So you know that it should be cosine theta, and 1 on the diagonal, and the rest should be 0.
Okay, so would you like to put 0 here and here? Yeah. That's true, because then we get rid of this. So now we basically have a 2D rotation matrix here, which acts on the x and y coordinates. And then we have an unchanged z-axis. Yep.
It should be minus for the second time because the even or the end. Remember, it's called it's going to be shifted in negative x.
That's correct. So we need a sign here as well. And so one argument, as you say, is to look at this geometrically. But another argument is to remember the fact that we need a matrix which with determinant of 1. And if we don't have the minus sign here, we're not going to get 1. So this is now the complete D matrix. So if we look at it, it's basically a 2D rotation here in the upper left corner, which acts on the coordinates here in the plane, x and y. And we leave the z-axis invariant. And so it looks like this. Okay, so following the same line of reasoning, what would z look like? So keep in mind that, again, we're actually dealing with a 2D rotation. One axis remains invariant. Well, we can consider the upper row to begin with. So the upper row corresponds to the transformation of basically xi into xi prime, where it says how does xi prime depend on these original coordinates. Well, we know that xi prime is equal to xi, so it should just be a unity transformation, similarly to the z-axis in the previous case. Okay. And for the rest? So for the rest, we have exactly the same as over there. Like this. Because we're doing a rotation in the eta zeta plane here, so only the two latter coordinates are affected. And they're rotating to the eta prime and zeta prime here with an angle theta. So one coordinate remains unchanged, and for the rest we have a 2D rotation matrix, and this also has determinant 1. And then finally, to write down B, well, it's the same thing here. We have one axis that remains invariant and just a 2D rotation for the other coordinates. So the row corresponding to this coordinate should remain, should have the same form as here, just a 1 and the rest zeros. Like this, because the last coordinate, zeta prime and z prime, are the same. So it's just 0, 0, 1. For the other two, we have a 2D rotation matrix again. So these are our rotation matrices. Their form is rather intuitive. We can sort of reason our way to how they should look based on the geometry of these coordinate systems. And so then we know that the total transformation going from the unprimed XYZ system to the primed XYZ system is just a product of these matrices. Now the product doesn't look quite as nice. It's a quite large matrix. And here is one of the sort of advantages of the mathematical tools we introduced previously. Because when we get A, which is a very large matrix, and let's say that we're then interested in finding the inverse transformation, sort of going back from the prime to the unprimed system, well then basically we should find A inverse. And if you have a large matrix you want to find A inverse, well there goes your day. But for orthogonal transformations, we know that A inverse is just A transpose. And interchanging the rows and columns, well, that's easy. Much easier than inverting it sort of in the standard way. So these Euler angles, phi, theta, and psi, can be used to describe a general rotation with individual matrices B, C, and D, and a total transformation equal to the product of B, C, and D. All right, these rotations that we've been concerned with so far have been arbitrary. We've considered a rotation with an angle theta, for instance, without any restriction on the value on theta. It could have been large, like pi half or something like this. So we're now going to move on to a topic which is known as infinitesimal rotations. And these are useful because, in contrast to general rotations with an arbitrary magnitude of the rotation angle, the transformation matrices corresponding to infinitesimal rotations commute, so their order can be interchanged, in contrast to general transformations. I don't know if you find this intuitive or not, that the order of the rotation actually matters, but we can see this by an example. So imagine we have some coordinate system and we have some object in this coordinate system. We consider some arbitrary object, like this. So what I would like to do now is 2 successive rotations. And after that, I would like to do the same 2 successive rotations, but in opposite order, and see if we end up with the same. So the first thing is to rotate this system 90 degrees around the z-axis. Sorry, let's remove the primes here. So 90 degrees about the z. We should then get this. I'm rotating the system like this. And the next rotation is 90 degrees around y. So I'm taking this, rotating it down like this. So this is the final coordinate system, in which there is some arbitrary asymmetric object. So let me now do the same thing, but just in opposite order. So I first rotate the system 90 degrees around the y-axis. So the z-axis goes down here, and the x-axis goes down here. And then I should rotate the system 90 degrees around the z-axis. And you see that what I end up with is different from this case. Even though I use the same operations, just in opposite order. So the order of rotations matters. But it's possible for us to introduce infinitesimal transformations which do commute. And an infinitesimal transformation looks like this. We'll go from the original system, the primed system, say, to the from the unprimed system, to the primed system by letting this matrix epsilon act on the vector in the original system. And we assume that the elements of the epsilon matrix are very small. They're much smaller than 1. So in matrix form, we can write it like this. And you see that this is equivalent to our previous notation if you just call this 1 plus epsilon matrix A. So this is a transformation matrix which we write as the identity matrix plus something which is small. So because this epsilon is small, the actual transformation, we call this infinitesimal transformations. So let's now consider two successive transformations to see if the order really is unimportant. Two successive transformations would look like this, where epsilon 1 and epsilon 2 correspond to the two different rotations. So these are matrices. When we multiply them out, we have to consider their order, because we know that in general matrices do not commute. So the result is this, and then we get something which the rest of it is of order epsilon squared or higher. No, not higher, just epsilon squared, sorry. Okay, so let's now try to interchange the order of the transformations. Like this. So you see that as long as we neglect these higher order terms, these second order terms in epsilon, these two operations are the same. Because epsilon 1 plus epsilon 2 is equal to epsilon 2 plus epsilon 1. So one advantage of these infinitesimal rotations is that they commute. But they have another quite nice feature. And that is that the inverse of an infinitesimal transformation is just 1 minus epsilon. And to see this, we can consider the product of the transformation A and the inverse transformation, because we know that this should be equal to 1. So we see that this is the case, since these two terms cancel. Okay. Now we do know one more thing about orthogonal transformations in general, and that is that the inverse of the matrix should be equal to its transpose. And so let's see what kind of consequences this has for our epsilon matrix. Well, the transpose of A is just 1 transposed, which is equal to 1, the identity matrix, plus the transpose of the epsilon matrix. And this should be equal to the inverse of A, which is 1 minus epsilon. And so we're led to the conclusion that the transpose of epsilon has to be equal to minus epsilon. Or written in component form, and this is a special type of matrix. Namely, it's an anti-symmetric one, because we say that epsilon ij is equal to minus of the element you get if you interchange the rows and columns. So for an infinitesimal rotation, this epsilon has to be an anti-symmetric matrix. Okay. So let's try to work with that. We know that epsilon is anti-symmetric. And if it's anti-symmetric, I should be able to write it as follows. The diagonal has to be 0, because epsilon ii should be equal to minus epsilon ii, which only has the solution 0. And for the rest of the elements, well, we just write some symbols. So if we have a value here, minus d omega 3, d omega 2 and minus d omega 1, well, then we immediately know what this side is due to the anti-symmetry. So this form should be completely general. And I've written infinitesimals here because we have assumed that epsilon ij is much smaller than 1. It corresponds to an infinitesimal rotation. So with this epsilon matrix, we can now say something about the difference between the rotated vector and the original vector. And we can denote this as dx, so the infinitesimal change in the vector as it has been rotated. And from this formula, we see that it's equal to epsilon x. All right, so let me try to write this out now. For the first element, dx1, I should take this row of epsilon and multiply it with x, which gives me that. So I've just written out this equation here. Okay. So let me reveal to you that there's actually a specific reason for why I chose this seemingly arbitrary notation that I just said sigma 3, sigma 2, and sigma 1 up here. Because by doing so, we should be able to identify a pattern in this set of equations. Do you see any pattern?
Looks like the cross product.
Mm-hmm. How do you see that?
Follow the indices, you see that it follows the Lewis up as well.
Yeah, exactly. So you basically have x3, you have the third component of a vector multiplied with the second component in a vector. And then you have minus the second component of the first vector multiplied with the third component of the last vector, etc. So you have sort of a cyclic interchange here, accompanied by a sign change. So exactly as you say, we can write this as, okay, so I used r vector here instead of x, just to indicate that we're dealing with a vector. So dr, if r is equal to x1, x2, x3, can be written as the cross product between some vector here and r. And this is a general property of infinitesimal transformations based on this form. So we can always write the infinitesimal change in the vector being rotated as a cross product like this. So this quantity d omega is a differential vector, which means that we should be able to write it in general as a vector indicating its direction with some magnitude, which should be infinitesimal. So something like this. We have a unit vector indicating its direction and then some infinitesimal magnitude. Okay, let's take a break.